is short and fat. Or, you see this? So this was a revelation moment for me in the Mechanics of Materials course on Tuesday, and I showed this to the students, and I realized I was just going to talk about the diameter change. But in addition to the diameter change, there's the length change. I don't think there's any book that tells you this explicitly, and it took me so many years to just realize that the effects in a transducer or a strain gauge is twofold. It is the Poisson's effect, right, of the reduction of area, but longitudinally this sensor is attached to the material that is being deformed through the glue. And I think this is really cool, because I just realized it, and I didn't pay attention to it before. Now, the best way to learn is to have moments like this. That's why I wanted to share. Any questions or comments about this so far? Who thinks that this is interesting or cool? Okay. Now today we're going to cover something else, which is the semiconductor physics, which is also very interesting. We need to give more definitions. So the current density, J, is equal to sigma, the conductivity, electrical conductivity, times eta. And eta is electric field potential, which is V over L, or voltage gradient. And this is another way of writing down the Ohm's law. So the current density is equal to the current divided by the surface area, and it is like a flux. So this is the advantage of representing this Ohm's law in this way. And what classes of materials do we know? Three major ones: metals, ceramics, and polymers. Okay, so let's have a look. It is expressed as ohm meter 1 over ohm meter. Okay, and you can see that for conductors, it's like 10 to the 7th or 10 to the 8th. It's a huge number. How many millions is this? Like 10 to the 6th is how many millions? 6 zeros is how many millions? 1. Okay, and 10 to the 7th is how many millions? 10. And roughly, we have 6.7, let's say, is another 10. We're looking at a number that's close to how many millions? Almost 168, whatever. You see my point? 100 million. Just hold on to that number in your head. Ceramics, 10 to the negative 10 to 10 to the negative 11. Concrete, 10 to the negative 9. Aluminum oxide, 10 to the negative 13. It's on the opposite end. You see the point? Even more. So it's like 100 million plus on one side, and it goes down to like minute, tiny value. See that? Very small number. Okay, polymers, 10 to the negative 14, 10 to the negative 15, 10 to the negative 17. Which means that these materials are doing what with electricity? They don't conduct. They don't conduct electricity, right? Does everybody see that? Okay, so metals are conductors, and ceramics and polymers are insulators. What does that mean? It means that, don't try this at home or ever. It means that if I take this permanent marker and I stick it into the outlet, which I'm not going to do because it's moist, so, who knows. but technically nothing should happen. All right? Now, if I take that piece of graphite, if I take a pencil and I stick it in the outlet, I don't know. What can I stick in the outlet? How about a key to my office? Maybe not. You don't want me to do that, right? I'm not going to do that. But let's say I take this rubber, or I take, what can I stick in the outlet? Paperclip. That wouldn't be that much different than this key. Anyway, there are more keys here. I'm not going to do any of that, and I don't encourage you to do that. But this is a very fast way to determine if something is a conductor versus an insulator, right? Because one is conducting electrons in the millions, and another one is not conducting anything. Now, what about semiconductors? You see the range? And what is a semiconductor? A weak conductor. What world do we live in? Material. Can somebody say we're living in the silicon world? Not silicone, silicon. Different pronunciation, totally different meaning. Okay, all of us are carrying the device that has a processor, and I brought that wafer last time. I passed it around. Let's continue. Do a conductivity problem. What is the minimum diameter of the wire? This is a copper wire. It's 100 meters long. 100 meters is going to be what? Roughly what? 300 feet? What do you think is the distance from here towards those doors? See, as an engineer, you should be able to do back of the envelope calculations. So I would assume that my I would say about 30 meters, maybe. The length of this auditorium. So 100 meters would be 3 times this distance, okay, roughly. I want you to put this together. So the length is 100 meters. The current is 2.5 amps. And the voltage has to be less than 1.5 volts. Okay? Resistance of copper is equal to L divided by A divided by sigma. This is electrical conductivity of copper that is given to you in a table for copper, pure copper. And then the current is 2.5 and the voltage is 1.5. So we can solve this from the area. And the wire is a cylinder, so its cross-sectional area is pi r squared, or pi d squared over 4. And we can solve for d, and the diameter has to be greater than 2 millimeters for the current being less than 1.5 volts. Okay, so this is a metal and this is a conductor. Now, before we do semiconductor physics, which is great, we're going to do semiconductor physics. What I was going to say is, what is the material science approach to control process, to control the structure to control the properties. Now we're talking about electrical properties. Copper is used as a wire. The function of a wire is to conduct electricity. In China, they have a high-speed train. In Japan, they have a high-speed train. What is a high-speed train? How fast can it go? (300 km/h), 400 km/h. So they have the infrastructure where they can go from one city to the other almost in the same time that it would take to take a plane, because you don't have to spend 2 hours at the airport for security and all that. How is that train powered? You know? How is the train in China powered? Is it running on gas? It's electric. How does the train get electricity? Through a laser? How? Through a copper wire. What I was trying to find is that copper, pure copper, is the best conductor that we know. But the problem with copper is that it's soft. So what happens once the train that is traveling at 300 km/h, I think the capability is actually much higher than that. I think they can travel at 300 mph, but because of the accidents and controls, they lower it down to 300 km/h. Anybody have been on a high-speed train? No? Anybody has been in San Francisco? Anybody has taken BART? No? Well, one day. Not trams, but the BART that can go from Livermore to San Francisco downtown. Yeah, it's called BART. To control the process, to control the structure, to control the properties. This is the structure. But everything is compared to electrical conductivity, and it's determined as a percentage of copper. So the problem with copper is that you can add a whole bunch of other stuff that's going to increase the properties, like hardness, to make it harder material, but you're going to jeopardize the strength. Okay? So we're optimizing on two parameters. One is the electrical conductivity, and the other one is the strength. So the other thing that happens is once the train goes at a high speed, there are some sparks. Have anybody seen an electrical spark? That contact gets oxidized and some of the material is removed. It's locally melted. That's how high the temperature gets in the electrical contact. Any questions before we move on into actually discussing the mechanism of how the electrical transport is happening in materials? This is the electron band structure of 1s electrons versus interatomic separation and interatomic space. So this is 1s electron and this is 2s electron state. How is current transmitted? What is the carrier of the current? Electrons. Okay. So to attain that transport, somehow, the electrons do what in a metal? They come closer to each other. They travel large distances. Okay, so if we look at the energy, this is equilibrium interatomic spacing. What we see is that depending on the electron structure, sometimes there is a gap, and it's called energy band gap. This is the energy band here, and this is the energy band gap, which means that in order to have transport of electrons, this electron here from this energy state has to come over here into this energy state so that it contributes those electrons to the conduction process. Okay. We established that the transport of the current is transported by the electrons, and the electrons have what? What do electrons have? And charge. They have charge. That's very important, right? Okay. So if we look at conductors, these are the filled states, and then there are empty states. So the electrons could jump into those empty states. And in order to become conductive, they have to either overcome this gap, or sometimes there is no gap because they're overlapping. So where do those electrons get the energy to do this kind of jump? Well, there's some thermal energy, and they can be excited into the empty higher energy states. This is the term used scientifically. Excited electrons. Are you excited? Okay, so as long as you stay excited, you can become conductive electrons. So there are two types of band structures: partially filled band and the empty band that overlaps filled band. And this is for metals. And remember, when we talked about metallic bonding, what was the term? Did we use the term C, electron of electrons? Electron C? And what does that mean? An electron pool. And I ask you, what is the average mean free path of an electron? Mean free path means that the electron travels without impinging with either other electrons or atoms, right? But how does this process actually happen? This electron cannot come from the filled bands. It has to be in the conduction band. So, the difference between a metal that's a conductor and an insulator is that this gap is what we say wide. Okay, and wide is how much? It means that it's greater than 2 electron volts. And that means that only a few electrons can be excited to go there into the conduction band or the empty band. Okay? So this is the difference. That in metals it's like a road. But for insulators, there's a roadblock, so they just can't get over. And then if we go back to the actual values, we see that the difference between a metal of 100 million and millions on the opposite side, but you know, it's not like you can say it's not like it's negative. It's not. It's just a very small number, right? But everything is compared to a million, and million is how many zeros? So what is that called? A million is a mega. I was going to say kilo, mega, giga. A million is a mega. So please remember that. What's a good analogy? A good analogy is pizza for everybody in this class. And we're going to order pizza. And each one of you is going to pay $1. Okay? So you're passing on $1 from you to your neighbor, right? And you two have no problem, right? You can just give her $1. Right? But what about you? Who are you going to give the $1 to? It has to come forward here to, eventually. So can you reach over there and give $1? Okay, all right. You see the difference? You need to be excited. Both of you need to be very excited. But there's an energy gap. Okay? So that $1 is an electron. We're all going to collect and order pizza for everybody. Okay? I just made this stuff up, this analogy. I don't know if it's good or not, but I hope it is. Okay. Now, semiconductors. Semiconductors, we said, are somewhere in between, right? So they're like 1, 2, or maybe 1/10,000, 1 millions, or like not as much as this, but somewhere in between, right? This is the conductivity of the semiconductor, somewhere in between. And they actually depend on the material very, very much. So, as a result of this, in semiconductors, the band gap is called narrow. And narrow means that it's less than 2 electron volts. But if there are electrons with enough energy, they can get excited to cross the gap. And there are low electron energy at lower temperature, and there's a high electron energy at high temperature. Remember, because everything depends on the temperature, and we learned in this class that this dependence is exponential. Right? That magic EXP, the E is E to whatever power. Okay. This is a plot that shows resistivity versus temperature. And you can see that this is 0, and this is room temperature somewhere, and this is pure copper in 10 to the negative ohms per meter. And this is pure copper. As we add more nickel, 1%, 1 atomic percent, you can see that it is increasing. On top of that, what we do is for processing, to control the structure, to control the properties, to control the process, to control the structure, to control the properties, we are deforming that wire. So on top of adding nickel, we're also deforming it, and then it goes up to even a higher value. And what we want is we have pure copper that cannot be used in the application of a high-speed train, doesn't have enough strength. We add nickel, and then we deform it. But as a result, the resistivity is increased a factor of 3. And the resistivity is increasing here with temperature, with more impurities. So it consists of thermal impurity and deformation. Why? Imagine I have a free path. Remember how I measured the length of this room? I have a free path. Over here, Maybe if I'm a little mouse or a cat, I do have a free path in between. So it depends on the size, right? And in the material, we have grain boundaries, we have dislocations, we have impurity atoms, we have vacancies. They all scatter electrons. They are preventing for the free path, which I'm taking now. But here, you know, I wish I could, but it becomes harder. You see that? I could, but it's harder. So this transport of electrons is by all those grain boundaries, dislocations, impurity atoms. What did we do here? We added nickel. It's a different type of atom. And on top of that, we deformed it. Deformation does what to the structure? Reduces the what size? The grain size. So once the grain boundary is met, see, I'm walking, and then this is the grain boundary. So now I have to like hop over this to continue my motion. Or I have to go around. And you can see if I had 3% nickel, it goes up even higher. So this is a balancing act between making sure that the material is adequately strong and at the same time it is conducting. And so far we talked about conduction of metals. We just barely touched on the semiconductors, and we said that they have narrow band gap. So I want you to remember this band gap of roughly 2 electron volts. And here is our Chinese train problem. Estimate the electrical conductivity sigma for a copper-nickel alloy that has yield strength of 125 megapascals. Now I want to ask you this, where is this coming from? Where is this requirement coming from? Very often in the problems, and I felt it as a student, is like you're being asked a question and you're given some data and you're like, why? Where is it coming from? So from the practical terms, where does this 125 megapascal strength comes from? Okay, and if it's less than 125 megapascals, what's going to happen to the wire? It will do what? If it's lower, it won't break. No. What is yield strength? No. This is let's get to it. What is the yield strength? It's the strength at which material, yes, or yields. Okay, so you want to avoid that. Why? Because after you deform the material to the plastic region, it relaxes and it's not keeping its original shape. It becomes longer. You don't want that. So it did not physically break, but imagine the wire that's hanging, you know, along that train that's going 300 miles an hour. You get the point. Okay. Now, we have the plot that shows the yield strength versus nickel concentration. So we see 125, and to get 125 megapascal yield strength, the nickel concentration has to be 21 weight%. Then there's another data that shows resistivity times 10 to the negative ohm meter as a function of the concentration. So we go here at 21% and we see that it is 30, 10 to the negative 8 ohms meters. And the conductivity, you're being asked what is the conductivity? It's the inverse of the resistivity, so we get 3.3 10 to the 6, 1 over ohm meters. Okay, and now you see how the strength is all of a sudden related to electrical conductivity. And that is measured compared in percent compared to pure copper. So whatever electrical conductivity of pure copper is, it's going to be compared to that. And what is the conductivity of pure copper, or resistivity? It's, what is this? This is 10, right? So this is 5, around 3, right? So you can see that the conductivity of pure copper is how many times higher than this? Because it's 1 divided by 30, right? And for this, for the pure copper, it would be 1 divided by 3. A factor of how many difference? No, a factor of 10. Where do you get the middle? You wish. You wish. Well, it's 3.3 10 to the 6. If you divide it by 30, okay? It's 1 divided by 30, okay? And then over here it is 3. So if I take it and divide it by 3, then this is going to be 10 times more, right? A factor of 10 difference. A factor of 10 difference is a big difference for something like conductivity. Are you guys with me? Are you following? This is not too complicated or too hard so far? Okay, good. All right, well, we said that for conductors, the carriers of charge are electrons. Have you heard about a hole? And can you tell me if you heard what is a hole? What's a hole? What's a hole in electrical terms? Can somebody tell me in layman terms? Huh? Why is it positive charge? Okay. Yeah, it's okay. Well, let's just think. There's no electron. So if there is no electron, it means that there's a spot, like here. I can take a spot. Now I can sit here because it's empty. All right. Let me see what you're reading here. Okay. 2 types of electronic charge carriers. Free electron. It's a negative charge, and it's in the conduction band. Okay, so the hole is, see, it's very simple. The hole is that if the electrons gets excited and goes into the free electron conduction band, and it leaves a spot behind. Like I left, you can take that spot. See that? So the hole in the valence band. What's the definition of valence band? Okay. And then, can you imagine that this doesn't happen instantaneously, right? They would have to like physically move, right? And we treated electrons as both particle and what else? A wave, right? Now, one thing that is kind of tricky a little bit is that the electrons and the holes move at different velocities. So we call it drift velocity. Don't ask me why. I'm not going to like talk about quantum physics and all that good stuff. And just take it as a fact that the drift velocities are different for the hole versus an electron. Okay. That brings us to what's called intrinsic semiconductors. And intrinsic semiconductors are pure material semiconductors, such as silicon or germanium. And they're all in group 4A in the periodic table. Then there are compound semiconductors. And compound semiconductors they're called 3,5s, gallium arsenide or indium antimonide, or 2,6 compounds as cadmium sulfate or zinc telluride. You understand the difference between pure versus compound. It's pretty straightforward, right? But the wider the electronegativity difference between the elements, the wider is the energy gap. For insulators, again, the gap is so high that the energy for the electrons to go into the conduction band is very, very high. It does not mean that it cannot happen. If the potential is very high, there's going to be what's called dielectric breakdown, which is associated with a violent process, which is almost like an explosion. In other words, you apply such a high potential, and sometimes it's tens of thousands of volts, which sometimes we have it in the grid. That's why the insulators are used for the electrical wire that transports the charges through the wire grid to the transformer that eventually goes to your house, goes to this room, powers the lighting, powers the computers and everything else we see. Okay. This is a silicon atom. This is a representation, a cartoon. And these dots here are electrons. And there's no electric field that's applied. Then we applied electric field, a plus here and a minus here. Do you remember the saying opposites attract? Okay? And the opposite is true, as similars are repelled. And if electron is leaving here, and it leaves a spot, it creates a hole. And as a result, one side gets positively charged and another one gets negatively charged. Because there's what we call a charge separation. And both start to travel in their respective directions. But their velocity, as we discussed earlier here, the drift velocity is called, they're different. So they're moving at a different velocity. And as a result, the electrical conductivity has two carriers that are contributing to the charge transport. One is the electron. So this M is the number of electrons per cubic meter. It's the concentration of electrons. What is E in given like this? No. The charge of an electron. What do this vertical, what do you call it? Absolute value. Okay, so here it is just the absolute value of the charge plus the number of holes per cubic meter, the concentration of holes times the charge of an electron, because hole has the same charge as an electron, just the opposite side. That's why it's an absolute value times the hole mobility. You see this? This is the key for a semiconductor. Because for a conductor, all the conduction is governed by the electrons. Whereas for the semiconductor, we also have this Hall mobility and Hall contribution. Does everybody understand now what a Hall is? Okay, so the number of charge carriers for intrinsic conductivity for gallium arsenide, the number of holes is equal to the number of electrons. This is the definition of intrinsic semiconductor. And what are the intrinsic semiconductors? These are here, pure or compound. Let's calculate for gallium arsenide. It's equal to sigma divided by the absolute value of the electron charge times the electron mobility plus the Hall mobility. And we can plug in the numbers. So for gallium arsenide, it's 4.8 10 to the 24th per cubic meter. For silicon, it's 1.3 10 to the 16th per cubic meter. And you can see the orders of magnitude higher carriers in gallium arsenide. Did I tell you I worked for Motorola? Motorola makes a power amplifier. A power amplifier is a device consisting of, I think, several transistors, maybe 6, and it's about 2 millimeters by 2 millimeters. This is how big it is. And every cell phone has it. And it has 25 microns of gold on each side. And it used to sell for how much, do you think? Your phone is worth millions. Yes, it is hard to make, because those were 6-inch wafers, and they hired me as an SAM engineer to support fab that was doing gallium arsenide. Back in the day, it was retailing for whooping $2. $2 freaking dollars. How is that possible? And one wafer, 6-inch wafer of gallium arsenide, how much do you think that cost for the raw material back in the day? Gallium arsenide. $10 is for a silicon wafer. You can buy a silicon wafer of this size for $10, 4-inch. And gallium arsenide wafer, 1,000. How about 1,000? $1,000 for a 6-inch wafer for gallium arsenide. Because it's a pain in the ass to grow a single crystal of gallium arsenide and then polish it, and it's very brittle, so it breaks and you need to make profit. But silicon wafer is $10 for 6-inch or whatever, 4-inch. Gallium arsenide is 1,000. And then, do you remember that wafer, 200 millimeter wafer I passed around? How much was the processor there? One processor. Somebody built themselves a computer, paid $500 for the processor. So one chip that was about this big was about what? Several $100. I'm telling you that on a wafer, that starting cost is $1,000, but it's 2 by 2 millimeters like this, the device sells for $2. And they're making money on it. Why is that crazy? This is the whole point. It's so little, so on a 6-inch wafer, how many devices are you going to have? Probably a lot, and you can calculate how many. Once I have seen that personally, I'm like, it can't be right. But it is right. So the problem with those gallium arsenide wafers, you know what was the problem? Gallium arsenide is very brittle, so it would break. And that device would also break. Next semester, I'm scheduled to teach fracture mechanics. And we discussed that. a little bit when we talked about fracture. You can either measure the crack length, if you can, but if you cannot, like in this tiny little thing, 2 by 2 millimeters, you have to test it mechanically to crush it. And then you would develop Weibull statistics. At which strain, at which level of the stress and force it breaks up. And then you back calculate the stress, and then you try and get crack length, and you're trying to reduce it somehow. Okay, the number of charge carriers. This is the conductivity of pure silicon as a function of temperature. Intrinsic carrier concentration. This is the equation. Again, what is the difference between what the intrinsic semiconductor? N sub I is what? Is the total number of carriers, right? They have different mobility. Electron and hole is different. But the number is the same. So this is the key of the intrinsic semiconductor, is number of electrons being equal to the number of the holes. And then we can calculate the number of carriers using that exponent minus E gap over KT. K is the Boltzmann constant, T is the temperature in Kelvin. And then for silicon, the band gap is 1.1, germanium is 0.6, gallium phosphide is 2.25, and cadmium sulfate is 2.4 eV. What is your practical range? Your device is working somewhere at the room temperature, so how does this device even work? I'll tell you. You know what it's called? It's called doping. How do you dope? What does it do? So for intrinsic semiconductor, the number of electrons is equal to the number of holes. N is equal to P. For extrinsic semiconductors, this behavior is determined by the presence of impurities that are introduced with excess electrons or excess holes. So the number of electrons is not equal to the number of holes. And there are two types of semiconductors. Extrinsic. N-type and P-type. And for N-type, we dope with phosphorus. For the P-type, we're doping with boron. And if you look at the electron structure of both elements, you're going to see that the phosphorus has 5 electrons. So this is 5 plus. But boron is 3 plus. So what does phosphorus give you compared to silicon? Protons. More acetylons. More electrons. Okay. And boron gives you more holes. Silicon is 4 plus. So here's a silicon, 4 plus, 4 plus, 4 plus, boom. Phosphorus, 5 plus. So there's an extra electron associated with it. And for boron, it's 3 plus. So it is going to take 1 electron from the silicon, which means that it's going to contribute a hole. Does that make any sense? So if you're ever in the business of buying wafers, which I have done on eBay, cheaper than what they sell them commercially. Silicon wafer is about $10. You can do many interesting things with it. but you need to know what kind of doping. Who dopes? Who is that doing that? The drug addicts. The engineers. You're the process engineer. So you need to know how much phosphorus you need to put, or how much boron you need to put in your silicon while you're growing it. So the wafer I brought you last time was a 200 millimeter wafer. I want to show you the ingot of silicon before it is sliced into wafers. Look at that. You see this? This is single crystal silicon. So you can see a human hand, so you know. And lengthwise, this is the actual growth process, where it is very slowly pulled from a liquid solution. You slowly, there's very high temperature, very precise temperature control, and very slow rate at which you're pulling it out, so that the atoms have enough time to arrange in a single crystal. And then after you get this ingot, it is sliced. You know what really blows my mind even now? What blows my mind, guys? It's all because of silicon, by the way. Try to do it without any chips. What blows my mind is the precision of manufacturing. The precision of that 200 millimeter wafer is down to almost atomic scale. Can you tell me how it's done? Because I still don't believe it. What do I mean by that? I mean that the control of the thickness of the film across this wafer is down to 1 atomic layer. Still blows my mind. Okay, extrinsic semiconductors, conductivity versus temperature. Doped silicon. This is doped silicon. It's a plot of conduction electrons versus temperature. And you can see that the curve is heavily nonlinear. There's a freeze out point, there's extrinsic, and then there's intrinsic. And you can see that the conductivity is increasing with doping, and it's because the imperfection sites lower the activation energy to produce mobile electrons. But here is intrinsic conduction. This is the doped conduction. You see what it does? If we were to rely just on intrinsic semiconductor properties of silicon, you would start to use it at 500 degrees Kelvin. Too hot. So doping allows us to get into the room temperature applications. The doping level is 10 to the 21 per cubic meter for N-type. Below 100K, there's a freeze out, and the thermal energy of electrons is insufficient for any conduction. Between 150K and 450K, there's extrinsic, and then it goes back to intrinsic at higher temperature. So this is what doping does. You can take a course in semiconductor physics that does this in detail, and I hope that you understand what I'm trying to explain to you. For intrinsic semiconductor, the number of carriers of electrons and the holes is the same. Doping changes that. And we either dope with the other element that gives excess electrons, and that's why it's called N-type. N is for electron, versus the one that is missing an electron, like boron, and then it is P-type. So the concentration of carriers is much larger than the number of electrons. The concentration of holes is much larger than the number of electrons. Yes? Okay. PN junction, or PN rectifying junction, or in layman terms, diode. What's the function of a diode? It's a one-way valve. In fluids, a flapper valve. Does anybody know what a flapper valve is? Imagine there's a pipe, there's a flapper, and the flapper works like this. So if the fluid is flowing in this direction, right, it's pushing the flapper and the fluid goes through. But if for whatever reason the pressure is higher on this side and the water is trying to go this way, the flapper locks the pipe and the water doesn't flow. Why would you need a flapper valve? Ever? Who's the civil engineer? Anybody? Nobody from civil? Huh? You are? How about mechanical? Okay. It's kind of like a civil and mechanical combined, because if there's an air conditioning system, and if there's a multi-story building, and by the new code, each AC has to have its own drain line, right, because it condensates. But in older applications, they didn't have a separate drain line, and it's an older building which you cannot retrofit with an extra line, like, I don't know, in New York or in Florida somewhere that was built in the 60s, and they're all draining into the same pipe. So for whatever reason, there's some back pressure. The pipe got clogged, wasn't clean. What's going to happen to the water? It's going to rise up, and it's going to create head pressure. And then what's going to happen is going to go to the individual AC units. And then the AC unit is going to get flooded on lower floors, and it's going to propagate to the higher floors. So in order to prevent this from happening, there's a flapper valve. Okay, does that make any sense now? Okay. Don't forget about flapper valve. It's cheap, and it's a good way to prevent flow in the opposite direction. So before we move on to the physics of this, there's a device, electrical device called a diode, which only allows current to pass in one direction, but it doesn't allow the current to flow in the opposite direction. What's the application of that? How can it be used? All right, I'll ask you a question. What is direct current and what is alternating current? Or are you familiar with AC/DC? A rock band? what does AC stand for and DC stand for? AC, DC. Alternating current and direct current. What kind of current do we have in the outlet? I'm being very direct with you. It's not. It's AC. It's alternating current. What does that mean? It goes from plus to a minus, plus to a minus, and a plus to a minus with a certain frequency. What is that frequency? In the United States of America, how fast does it change the polarity from plus to minus? 60 hertz. Yeah, you remember, okay. But if you go to Europe, what is the frequency there? It is 50 hertz. And 1 hertz is what? 1 per second. So this is the frequency of 1 hertz. And if it is 60 hertz, it means that the voltage goes from plus to minus 60 times in a second. Okay. What about the voltage in your cell phone or your laptop? Have any idea? Battery. It is direct current. So how do you get the voltage, or how do you get the current from alternating current to the direct current? Because you need this conversion to charge your cell phone. You use a flapper valve, meaning that 60 times a second this flapper valve opens and closes, opens and closes, opens and closes. And what you're doing is you're pumping of the current only in one direction. Okay? So with just one simple diode, which is a semiconductor device, you can do a conversion from alternating current to pseudo-direct current. Okay? Because it goes plus and minus. You chop off the minuses, see? And you only get the pluses. And because it is 60 times a second, it's kind of like steady flow, almost. So I just explained to you the physical principle of a diode and converting AC to the DC. Okay. We take a p-type semiconductor and an n-type semiconductor, and there's an interface between them. And when there's no voltage applied, there's no flow. But if we do what's called forward bias, meaning that carriers flow through the p-type and the n-type regions, the hole and the electrons recombine in a p-n junction, and the current flows in forward bias. But if we reverse the voltage in the reverse bias, the carriers flow away from the N junction, and it's depleted of the carriers, giving you very little current flow. That's what happens. This is the idea. And if we look at the IV curve, we do have conduction in the positive voltage and positive current, and then it locks up over here. And that's my alternating current on the top upper corner versus time, plus, minus, plus, minus, plus, minus. And if we just pass that current through that p-n junction, it only gives us the plus, and the minus is chopped. This is the idea of a p-n junction diode. So next time we're going to talk about a MOSFET transistor. And a MOSFET transistor is a PN junction with a switch, meaning that you can have it either conducting or non-conducting. And those states correspond to 1 and a 0 in a digital device, which is based on the physical principle of conduction, right? We live in the digital world, so that's where the digits come from. Signal versus no signal. That's very simple. Okay? And we'll talk about the physics of that on Tuesday.